All right, guys, welcome back to another day of EIGRP in our CCIE routing and switching discussion. Today we're going to be looking at covering several topics, all related to authentication within EIGRP. We've got classic EIGRP authentication that we're going to discuss, automatic key rotation. I'll do a demonstration about how we can configure automatic key rotation with our Md5 authentication process. And then we also have our named mode authentication that we're going to be discussing today as well. So we're getting close to the end of our 19.5 hours of EIGRP. And then our next session we'll probably take a look at EIGRP summarization and traffic engineering with summarization as well. All right, that's what our goal is today. This is the topology that we're going to be using for our discussion today. This is in the Google Drive under the classic authentication folder. If you want to grab it, you can, or if you want to take a look at it later on when you're going through the videos a little bit later on, you can certainly take a look. So this is the same topology that we use for our traffic engineering configuration. In this case, though, we're going to be applying classic configuration on router 1 with Md5 authentication. And then we're going to do some classic configs on router 2. And actually, we're going to be running named mode configuration here. So let me change this to AF config, because that's what we're going to be doing on this particular router. The reason I'm doing this, you normally wouldn't do this obviously in a production environment, but the reason I'm doing this is to demonstrate the idea that we have the ability to configure multiple authentication modes, and we can commingle these different configuration modes on our platforms. All right, I gotta add one here. All right, and we're gonna do show authentication on this guy here. And we'll do that on AF interface Ethernet 1.0. So we're going to be applying several different configurations in this case, and really just kind of taking a look. It's not really a complicated topic, which is why we're going to try and wrap up all three of them as part of our discussion. Yeah, that's what we're going to be taking a look at in this particular lesson here. All right, so let's go ahead and get started. Authentication is a pretty important concept when it comes to securing our control plane. We're going to take a look at classic and named mode authentication. The configurations are slightly different with the application of the configuration as well as the syntax, and even our authentication options will change as well. The reason why I would want to run authentication is there's nothing that really is going to stop anyone from sending stuff into our routing domain to affect our control plane functions. If multicast is being used to disseminate information and our switches are not configured with IGMP snooping, then that multicast traffic is going to be flooded throughout our broadcast domain, and people can take that multicast traffic and they can identify what's happening in the topology with our routing protocols. In addition, they can also inject rogue devices in the network and make unauthorized changes to our control plane routing. The key difference here in this case, and we are talking about IPv4, we'll take a look at IPv6 a little bit later on in a different lesson, but is that we're doing authentication and not encryption. Okay, let me explain a little bit about how this works in the concept of routing. It's very similar to what we would see in, say, NTP authentication or any other kind of MD5 or SHA-based authentication mechanism that we have. So we've got a router here, and this router wants to send out routing updates over to router 2. Now, obviously, normally these updates are going to be sent out in plain text, and anybody can intercept that information. And if they intercept that information, they can either modify it and forward it on, or they can just utilize that information to discover information about our topology. But what's worse is because we're not running authentication, somebody could actually insert a device into our topology, and then they could start to inject false or misleading information into our control plane to affect how things are going to get routed through the control plane. So ideally what we'd like to happen is we'd like R1 and R2 to be able to authenticate each other in this process. So just to be clear, we are talking about authentication. We are not talking about encryption, right? There is no encryption in this case. Now, if we do go to the IPv6 stack, we actually use the built-in IPsec framework in IPv6 to provide for both authentication and encryption in that process. So we're not going to talk about that this time. We will discuss it a little bit later on as an optional topic, but you guys are going to be primarily responsible for your understanding IPv4 authentication and encryption for the written exam as well as for the lab exam. So that's what we're going to focus our attention on in this lesson here. Like I said, it is something that we do want to look at a little bit later on with regard to how to implement encryption and how to implement authentication in IPv6. It's a relatively simple concept, actually. We might, if I have time at the end of this lesson, just pull up a configuration document and take a look at that configuration. But let's start by doing our IPv4 stuff first. So the way that this essentially works is we establish some keying material on each device, static keys that get configured, and we'll do that through the use of a keychain with key IDs and key strings. Let's assume in this case we only have a single key to make it simple. Each side has a key that gets configured, and whether we're running SHA or Md5, what's going to end up happening is we've got our hashing process that's running. We'll just say in this case Md5 on this router, and we've got our hashing process that's running on this router as well, Md5. And whenever I send out a routing update, that routing update, let's just say it's an update, right? This would apply, by the way, to every single packet type that gets sent across the network. Hello packets, queries, replies, acknowledgements, everything that gets sent in EIGRP is going to be have this authentication option applied to it. So I take this update and I run it through the hashing process. I take my key and I run it through the hashing process with the update, and out of that hashing process I'll get something called a message authentication code, or a MAC. This is essentially the hash that's going to be sent across the channel. So I'm going to go ahead and send that hash along with the update. So this is the MAC, and there's my update right here. I'll just put UP. And when the router receives that information, it's going to take that update. It's going to, whoops, let me do that again. I don't want to confuse the situation here. So we're going to take that update. We're going to drop that into our hashing process. We're going to take the key. We're also going to drop that into the hashing process. And then out would come the MAC that's calculated on this side. And I'm going to take this MAC and the MAC that I received, and I'm going to compare those MACs. Are they the same? Right? Are they equal? If they're equal, then we've essentially authenticated the peer, because the only way that it was able to generate the hash is with the appropriate key. And then on top of that, we were also able to verify whether or not the data has been manipulated in midstream, because of if the data would have been manipulated, the output hash would have been different than what I received from my peer. So that's a basic concept. We never send the information across the channel. The actual keying material never gets sent across the channel. That's essentially how we provide authentication without encryption. All right. Now, in the case of EIGRP, there are actually two types of authentication available. In classic mode, we only have one type, which is Message Digest 5. In named mode, we can either run Md5 or we can run HMAC SHA-256. Now, the nice thing about HMAC SHA-256 is that it has a longer bit length. We had, in the case of Md5, maybe potentially some collision problems. A collision is a weakness in Md5 where two different plain text inputs will result in the same ciphertext output. And then also, both of these algorithms are susceptible to brute force attacks using rainbow tables because we don't use any salt values. The salt is essentially the key in this case, but it's a static salt. These algorithms are susceptible to brute force attacks using rainbow tables, which is just basically a dictionary of hashes that we can compare against. Without that key, though, that dictionary becomes useless, and rather than being able to reference the hash across the dictionary, we would have to recalculate each hash or the hashes with the update by rolling through a bunch of different keys, and it's just not really feasible in that particular case. Sorry about that. So the Md5, of course, is going to provide 128-bit key space. So SHA-256 is twice the key space. So we obviously want to use the SHA-256 when possible, but the problem with SHA-256 is that it's only available in named mode configuration. It's not available in classic mode configuration. But we're going to take a look at both. I'm not sure exactly what they would require you to do on the exam with regard to named mode. I know that when I took the exam, there wasn't any named mode configuration on the lab exam, but that is something that they could easily incorporate with a minor revision to the objects or the tasks that you're faced with in the configuration. All right. So with Md5 authentication, both classic and named are available. Md5 authentication is available in both of those modes of operation. We use these things called keychains, which is basically just an outer container for the keys themselves. And we can actually configure what we call automatic key rotation. We'll take a look at an example of that as part of our lesson today, where we specify the send and the receive lifetime of the keys. But with regard to key rotation, send and accept lifetimes, if they're not specified, either with the classic mode configuration or the named mode configuration, they're going to be infinite, sending and infinite receiving lifetimes. All right, again, SHA authentication is only available in named mode. There are no keychains in SHA authentication, so we don't have any automatic key rotation in this particular case. So this lesson doesn't really require a whole lot of background or theory. It's really just a matter of configuring and verifying, and that's what we're going to focus a lot of our attention on in this particular lesson. So let's go to our topology here. And the first thing I want to show you, actually let's make sure that we're running classic EIGRP on this router first. That way I want to demonstrate the interoperability between classic and named mode configuration. So you could potentially move from a classic mode configuration to a named mode configuration with authentication by simply running, by migrating the configuration. So let me do a show IP interface brief real quick here. Show IP interface brief. Looks like we're good to go on the interfaces. Serial 20, serial 21. Let me just verify that. Yep, 2021 and Ethernet 11. All right, let me do a show IP protocols. So we are running EIGRP in named mode in this particular case. So I'm going to go ahead and get rid of that. Show run pipe section router. And we'll just take out our named mode configuration. Config T. No router, EIGRP CCIE. All right, show IP protocols, we should be blank now. All right, so we've gotten rid of our EIGRP named mode configuration. So let me do a quick show IP route pipe include connected. And we'll do router EIGRP1 in this case. Let's do a network of 172.16.0.0 and a network of 192.168.1.0. Try that again, 192.168.1.0. All right, so we're now running EIGRP on our interfaces. Now what we're going to do is I'm going to show you how we create our keychains. Now actually, keychains themselves are not a direct relation to EIGRP. They're actually not configured under EIGRP configuration. They're actually considered to be part of kind of a generic configuration because there are many different applications in which we can use a keychain, including OSPF authentication. So the first thing that we would do to create a keychain is to do the keychain command. Give it, I'll just do a temp on this one because we're not going to use this keychain as part of our process. So who just joined in here? Somebody joined and left. Okay. Probably just switching from phone to PC. All right, so we've got a keychain. Now, if I do a question mark here, we can see there's not a whole lot to this. We can take out certain configurations. We can default certain configurations, but what we're going to be doing is we're going to be configuring a key. And you'll notice that we have to specify something here called a key ID. Now, this is a really important number because the key ID is what is going to be sent along with the packet and the hash to be able to identify what key is being used in this particular case. All right. Now you do have to be careful. There's a couple of other concepts with key IDs that I'm going to talk about as we kind of go through the process here. But the key itself does allow spaces. So you can say, for example, password. All right. Oops. Key 1. We got to create the key ID first, and then we'll specify the key string, which is essentially the unencrypted version of the password. So if I just put in the password, it can be unencrypted. We can apply service password encryption to these plain text passwords, so they could be encrypted using a level 7 encryption. But let's go ahead and just set our key to password. Okay. Now, if I do a show run, pipe section key, we can see the configuration of the keys, right? And actually the key ID and the key string is listed here. It's a pretty basic configuration, right? In fact, when we're seeing it, we don't really see too much about the key than the key in plain text here. Now, if I did my service password encryption, service password dash encryption. Let me get out of config mode. Config T, service password dash encryption. And if I do a show run pipe section key, we'll see now in the show run output that that key is now obfuscated using that level 7 encryption. All right. But here's the thing about the key itself. If I do a show keychain, all right. Oops, show keychain. There we go. You'll notice here that when I do a show keychain, the key still shows up in plain text. And also notice that there's a space at the end of that key, which indicates that it is actually the white space was actually allowed as part of the key string itself. This could totally be something that they would throw at you on the lab exam from a troubleshooting perspective, where you're looking at the basic configuration in show run and authentication appears to be working correctly, but they threw in an extra space in the key string to throw off that configuration. Now, you would be able to see a key mismatch in a debug. If you did a debug EIGRP packet or something like that, you would be able to see whether or not there was a key mismatch or a key ID mismatch between the different peers, which we'll take a look at a little bit later on. All right. Notice that the string itself is in quotations for that purpose, so that you can identify when spaces exist. So make sure you look for that. Okay. So that's our show run pipe section key chain. Spell it right, that would help. And we can see that. Now, as I mentioned before, we do not send the key itself across the channel in any case. Let me do key space chain, sorry about that. We do not send the key itself across the channel. We simply send the key ID. This is going to be sent as part of the EIGRP packet as part of the packet header. We'll take a look at that in Wireshark a little bit later on. So the key numbers are very critical between the two different routers. The keychain name does not have to match between the routers that are performing authentication. In any case, whether it's named or classic configuration, that keychain name does not have to match. But the key ID does have to match, because when the receiving router receives a packet and it references a key ID, the receiving router is going to use that same key ID to reference its local key to make sure that the authentication can take place and we can generate a hash appropriately. Okay. Now we also support with the keychain automatic key rotation based on key numbers and overlapping keys. We'll take a look at that configuration a little bit later on. All right. So we create our keychain, and then the next step of this configuration would be to apply the authentication to the interface level. All right. The keychain name, like I said, again, is locally significant, but the key IDs have to match. We're not going to apply this just yet, because what I'd like to do is I'd like to go ahead and look at the basic adjacency without authentication in this particular case. So if we go back to our topology diagram here, we're running address family configuration on these routers here, R4, R5, and R2, and we're running classic configuration on R1. We're not going to run any authentication on R3, but we do want R3 to be able to run EIGRP. So let's go ahead and configure this guy with classic configuration. In fact, let me put that in here. All right, so this router is going to have a classic config, and it's going to be running no authentication. The reason why I'm doing this, obviously, we would in our scenario, we'd want to apply the appropriate amount of authentication across the board. You know, a common authentication method across the board to all of our peers. But in this case, we're not doing that because I'm trying to demonstrate the idea that these configurations are compatible with each other. So we're running named mode on this router presently. Let's go ahead and take off named mode. No router EIGRP Ccie. And let's do a router EIGRP 1. And do a show IP route pipe include connected, just so I can see which interfaces to run. So we just could do a 172.16.0.0 here, and I should get an adjacency with router 1. Show IP EIGRP neighbors, and sure enough, I have an adjacency on both 2.1 and 2.0, and 2.1 or 2.0 is this peer. So let's take a look at what those hello packets look like on that interface, just so we can see if there's any reference to authentication in this particular case, and how that would change once we start to do authentication on other devices. All right, so it should bring up my Wireshark. There it goes. Here. So we've got a Wireshark running. Let me go ahead and just open up a packet here. Any packet is really fine in this particular case. Actually, you know what? Let me go ahead and grab a packet on, well, it's this interface anyway, so it doesn't really matter. We should be able to, it doesn't matter who it's coming from. In either case, we're not running any authentication. So here's our classic mode EIGRP configuration. And as far as the parameters go, we don't really see any reference at all to authentication in anything in relation to the hello packet itself. All right, so it's not that unlike OSPF where we see an authentication type essentially of 0. In the case of EIGRP, if we're not running authentication, we simply don't see a reference to authentication in the configuration itself. So that's what we're seeing here, basic EIGRP, standard K values. Now that's interesting that I'm seeing a K6, even though this is a classic mode configuration, right? And that's actually very interesting. And that probably has to do with the fact, well, let me see here. Let me make sure I'm grabbing the right information here. So I want to see the source of, in the case of the router here, on router 3, show IP interface brief. Serial, I want to see what's going over to router 1 here. So serial 20, which would be my 3.2 interface. I don't want to see what's coming from my 3.5 interface. It's interesting because in our topology here, if I go back to our topology diagram, we're running named mode configuration on router 5, but we're running classic mode configuration on router 3 and router 1. So if I go back to my Wireshark Capture, I'm essentially looking at what's coming from my 3.2 interface. This is what's coming from the peer, what I'm receiving, and this is what I'm sending. Sending and receiving, sending and receiving, sending and receiving. But what's interesting about this, I wouldn't have noted, this is unrelated to authentication. I just think it's really interesting that we're actually sending all the K values, K6 included, even though this is a classic mode peering relationship. I have a feeling that would be because we're running a mix. There's a router that we're peered with that's running named mode configuration, and there's a router that we're peering with that's running classic mode. Again, doesn't really have much to do with authentication. The point here is that we're not really seeing anything with in relation to authentication in this particular configuration. All right, so we'll go ahead and stop that Wireshark Capture for now, because we'll grab it again, but let's go ahead and stop it for now. We've got our neighbors. We've got without authentication. And by the way, that's what I would definitely recommend, is before you apply your authentication, make sure you have your peering relationships, and also make sure that your Q count is 0. Q count is 0 would mean, or it indicate that your your peering relationship is complete and you're fully converged, and you're no longer concerned about, or you're no longer in the process of sending and receiving different datagrams to be able to converge, and different EIGRP information to converge. So we see our adjacencies. We, of course, can see the hello packets. If I was to do some updates, inside those updates, I'll show you that a little bit later on as well. If I was to do some updates, in other words, trigger some sort of network to go down and come back up, I would see some updates, and the routing information would be contained in that update as well. The point here, and this is really the most important thing, is that the packet that's being captured is in clear text. So if somebody was capturing the frames, they're going to know what the routed network looks like. The downside to this process, though, is that even if we do enable authentication as part of our configuration, it is not going to change that behavior. Okay? It's not going to change how that behavior is. We're still going to be able to see everything in plain text in the configuration or in the exchange of information. So let's go ahead and set up authentication based on our topology here. We're going to do a classic authentication with a single key between router 1 and actually we're not going to do any authentication in router 3. So let's do a classic authentication configuration with Md5 on this router, and then we're going to do a named authentication configuration on router number 2. Okay, so I'm going to start with router 1. The first thing I'm going to do is I'm going to define my keychain, and let's go ahead and create an actual keychain that we're going to use. So we're going to say keychain Ccie, key 1, key string Ccie-1. Okay, no space at the end. All right. And of course, I want to go ahead and do that also on router 2. Now, this is the interesting thing about the key string configuration. Because it is routing protocol independent, it's configured exactly the same way. Okay, so we're going to go ahead and create a keychain, Ccie. Again, key 1, because they have to match. Try that again. I wasn't recording, but we just applied the same key string configuration to router 2, which is our named configuration. All right, so do show keychain. We can see the keychain here. Also notice that the accept lifetime and send lifetime are valid now and always valid. So if we're not specifying the lifetimes of these keys, they're going to be valid essentially for from the beginning of the configuration forever. Which brings us to an interesting question. What happens if I have more than one key and they're valid? All right. So if I have 3 or 4 or 5 different valid keys on each router, how is the router, what key is the router going to use to send its EIGRP packets? And that is going to be the lowest valid key ID. So if I have key 1, key 2, key 3, key 4, and they're all valid, I am going to send my EIGRP updates and hellos and whatnot with a hash using key number 1. Now, as far as reception of keys, I can match any key that I receive to any valid key that I have in my keychain. So with regard to receiving keys, I could receive a datagram that uses key number 5. As long as key 5 in my keychain is valid, I can then authenticate, and the key strings match, I can then authenticate that datagram. That's the EIGRP packet. All right, so just do a little cursory check here, make sure our keychains are valid. Do show keychain. And we can see in this case that key number 1, we're focusing on keychain Ccie, and it is valid. It is the right key ID, it is the right key string, and so on. All right, again, because we did not specify a send lifetime or an accept lifetime in this case, the send and accept lifetimes are automatically configured to be active as soon as you enter the key, and they're going to have an infinite lifetime. All right, so Mike has a question here. Does the key lifetime need to match up? They do, if they have a specific lifetime, which means that your clocks also have to be synchronized as well. We're going to take a look at that when we do some actual key rotation configurations in a little bit. It doesn't matter that the lifetimes have to match. Actually, I know what you're asking now, Mike. I apologize. So yes, as long as the keys are valid for sending and receiving, it doesn't matter if the longevity of a key is different on one router versus the other. It just simply has to be usable. So I might have key 1 on the left that's only valid for 3 months, and key 1 on the right that's only valid for 1 month. But as long as we're in that same window where the keys are valid, then the key lifetimes do not have to match. Okay? They just simply have to be usable. All right? So we've created the keys. Now we need to apply the configuration to the router itself. All right? In classic mode, the configuration is not quite as intuitive as it is in named mode, because again, we're doing this configuration at the interface level rather than in the named mode configuration, which is why named mode is still more preferred. So we're going to do this configuration on serial 2.1 in our classic mode configuration. So interface serial 2.1, and then we're going to simply put in IP authentication mode EIGRP1, so that's the autonomous system number, Md5, and then I'm going to do an IP authentication keychain Ccie, need to apply it to the autonomous system number Ccie. Now you'll notice that I did lose my adjacency with that particular peer. All right. In fact, if I do a debug IP EIGRP packet, debug EIGRP packet, we should see that we're receiving hellos and we're sending hellos. But as soon as let me do an undebug all real quick. So as soon as I receive a hello, I can see here that it's missing the authentication. All right, so we ignored the packet. Okay. So we can see from this output here that it's pretty obvious that that authentication is misconfigured, and a debug EIGRP packet would be how we would see that. Probably something that you're going to have to do at the lab, at some point. You definitely need to know how to interpret debugs and how to use the appropriate debug to make sure you're seeing the information that you need to see. All right. So in this case, we could do some additional debugs, but at this point I would say, okay, I'm sending hello. I received a hello on serial 20, and I'm ignoring the packet from 1.2 because it's missing authentication. So based on our topology diagram, we're going to go into router 2. We're going to apply the exact same configuration, but we're going to use our named configuration in this particular case. And it's a little bit more intuitive because we're actually doing it under the named configuration process. We're actually seeing here, we're not even running a debug on this side, and we're actually seeing here that we are getting an authentication failure on this side of the link based on, we don't know what that authentication failure is. It could be related to a misconfigured key ID, or whatever. All right. So in fact, let me do one more thing before we fix this problem. Let me go ahead and do a Wireshark capture on this interface to show you what the hello packets look like going out and what the hello packets look like coming in. Of course, the ones coming in are not going to have any reference to authentication. The ones going out will have reference to authentication. So we'll take a look at what's coming from 2.1. I believe it's 2.1 in this case. 1.1, excuse me. We'll take a look at what's coming from 1.1 and see what we see with regard to the authentication. All right. It doesn't really matter whether it's an update, a query, a reply, an acknowledgement, or a hello. They're all going to essentially look the same from the perspective of having that authentication. So let's grab a hello packet here from 1.1. The source is 1.1 here. And we should see in this reference that we have authentication now. So now you can see we have an authentication field. The key ID is 1. And this is the digest that was created in the process. You know, that diagram that I drew, that's the digest that was created in the process of sending that hello packet to the peer router. All right, so because we're seeing that, we know that we're running Md5 authentication. It's actually technically hex 2 is how we identify the authentication. And message digest 5, the key ID is key 1. We're not sending any of the keying material over the channel. We're just sending the resulting hash, which is essentially a hash of this datagram, of this packet, with the key itself. All right, so it's broken, of course. So let's go ahead and fix the problem now. We're going to go into router number 2, and we're going to go into our EIGRP Ccie configuration. Actually, let me make sure, because I don't think we've looked at this router yet. Show run section router. I believe it's still Ccie, yep. So we've got our named configuration here, Ccie, address family, unicast, autonomous system number 1. Here's our topology base. Here's our network statement, and so on. So we already have the named mode configuration applied. Now we're just simply going to apply, let me do a show keychain. I always like to do that just to make sure I'm getting the right key information. And router EIGRP Ccie. And we're going to go into address family IPv4, unicast, autonomous system number 1. And now we're going to go into AF interface. Now I could apply this to the default interface if I wanted to, but you'll notice here that in this particular design, we're going to be applying the authentication individually on each interface. On this router here, we're going to be using the default interface and a non-default interface in our AF configuration. So let's go into AF interface serial 21, and let's apply our authentication. It's essentially the exact same configuration, authentication, mode, MD5. The only difference here is we're not applying it to the autonomous system number because we're in AF interface, and that applies to the AF configuration. And then we're going to do an authentication keychain Ccie. Now, at this point, we should get our adjacency back. Yep, we got our adjacency back, and we're now talking back and forth using the same key ID with the same key string. If I do a show run section router, we can see that it's a much cleaner configuration because everything is configured under CCIE for EIGRP, as opposed to having these disparate or individual configurations that are applied to an interface. Now let me see something real quick here. If I go into interface, sorry about that, I lost my batteries there in my microphone, but I don't know what point we lost it, but basically I was showing you here that this is a nice clean configuration because everything is under router EIGRP. We don't have these unique configurations that are applied at the interface level and then other configurations that are applied at the interface level. Now if this was classic mode configuration, I would have gone into the interface and I would have applied the authentication to the interface as well as the keychain EIGRP1. And this is a little bit confusing because it looks like we have a classic mode configuration on the interface, but we're actually running named mode EIGRP. So in this particular case, this does not apply to the configuration. I doubt that Cisco will try to do something like that to you on the lab, where they kind of try to trick you in thinking, oh, this is not the right keychain because it should be keychain CCIE and this is CCIE1 or whatever, and it's applied to the interface. But the reality is that that configuration has no bearing on the overall configuration because we're not running in EIGRP classic mode. So any kind of interface type configurations simply don't apply. All right, now I would certainly want to clean this up, but the nice thing about this is it does give me the ability to move from one EIGRP configuration to another and then go back and clean up that particular configuration. All right, so I'm going to go ahead and clean that up anyway because I don't want it to be confusing when you guys are looking at the files a little bit later on. Because everything I'm doing here is saving to the configuration, so when you guys go open up the actual configuration, you'll see all the configs in the topology. All right, so if I do a debug IP or do debug EIGRP packet, we're pretty much not going to see anything here. The packets are going to be sent and received. The only thing that you would pay attention to here is that we're actually receiving a packet with Md5 authentication using key ID 1, and we're also sending a hello. Now, when we do our sending, we don't really identify that we're actually sending with a particular key. All right, we just simply say when we receive packets, we receive it with a particular key. But if I was to do my Wireshark Capture here, you would see that not only are we sending and receiving, in fact, we're already still doing the capture. So let me pull a hello packet of 1.2, and I should see in this case that authentication is being received as well. All right, key ID 1, there's the hash, and they're going to look slightly different. You can't really compare the hashes between the hello packets because they're formatted differently, so the hash output's going to be a little bit different. But remember, we're just receiving this datagram and we're trying to verify that hash against that particular datagram. All right. All right. So let me go ahead and let's kill the capture here so I can release some resources. And let's go ahead and do some other configurations here. So we're going to wrap up our configuration by going into router number 4 and doing a named mode configuration with a key string. In this case, though, I'm going to misconfigure my keychain just so we can see that we're actually receiving a key with a different key ID. There's really only 3 possible things that you'll see with authentication with EIGRP, specifically with IPv4, is either there's an authentication that's not configured. We saw that already, where we saw the message indicating that authentication was missing. There's a key ID mismatch, or there's an invalid key string. So actually, in this particular case, let me go ahead and set it up with an invalid key string first so we can see what that output looks like and take a look at that debug. All right. So we're going to go into router number 4. We're running name to mode configuration in this router already. We're only running classic mode on router number 1, but we've got to go ahead and verify it. Show IP protocols. And we are running classic or name to mode configuration. We've got our default K values. Everything looks good. We still actually have peers in this particular case. Because again, we're not running authentication as of right now on this serial 2.0 interface. So in fact, let me go ahead and apply that for router 1 on serial 2.0 and on Ethernet 1.1, because eventually we're going to go in. Actually, we're not going to do it on serial 2.0 because we're not running authentication on router 3 at all. That's the other benefit to doing authentication. All right, hold on one second. So like I said, the benefit of running authentication in EIGRP is that it is enabled on a per interface basis. So you could choose to run authentication, or you could choose not to run authentication. It's completely up to you. It's not a global. Authentication is not applied to the global routing process, is my point. All right. So we actually need to go ahead and enable authentication on Ethernet 1.1 in this case on router 1. So let's go ahead and do that. Quite simple, actually. We just simply take the configuration, show run interface serial 2.1, and apply that configuration to interface Ethernet 1.1, because we are using the same keychain and the same authentication mode. We'll lose our adjacency, of course, because we're going to be running Md5 authentication on the other side on router 4. All right. Now remember, what I was going to do in this particular case was I was going to go ahead and create my keychain, and we're going to use the right key ID, but we're going to set the key string to Ccie 1 instead of -1. And then I'm going to go into router EIGRP Ccie, address family IPv4, unicast autonomous system number 1, AF interface. And we're going to be applying this authentication to interface Ethernet 1.1. And we're going to do authentication mode Md5 and authentication keychain Ccie. All right. So if I go back to router 1 and I do my debug EIGRP packet, I should see now that I have invalid authentication instead of missing authentication. And we can see that right here. Right here we're seeing that we are receiving, let me do my undebug all. There we go. So we are receiving a packet. Let me scroll up right here. So I am receiving a packet. I received a hello from 3.2. And I'm ignoring the packet. Excuse me, this is the one that I'm looking at right here. I'm ignoring the packet from 2.2 because of invalid authentication as opposed to missing authentication. Remember, the other problem that we saw was missing authentication, which indicated that one side was running authentication, the other side was not. So we would actually see potentially both errors. Actually, you probably wouldn't see invalid. You'd probably see missing if I was running SHA on one side and Md5 on the other, or if I was running no authentication on one side and Md5 on the other. But in this particular case, we're seeing that we're getting invalid authentication, which indicates that the passwords don't match. All right, so authentication mismatch, even though the key ID is valid, I have a key 1. I'm unable to authenticate the packet against that key because of an authentication mismatch. Essentially what this means is that the hash failed. Going through that hash calculation failed, which means that there is probably a password mismatch in this particular case. Now, you could potentially see this if somebody is modifying the packets midstream. If you've got a man-in-the-middle attack and somebody's trying to modify or change the integrity of the datagrams that are being sent back and forth, it would manifest itself as an authentication mismatch, because that's essentially what's happening when the hashing process fails, when I try to verify my MAC against the MAC that was received. All right, so let's go ahead and fix that problem. Show run section key and config T, key chain Ccie, key 1, and key string, let's do Ccie-1. So now we should get our adjacency, and if I do a show run section router, I can see that the authentication is appropriate now. We have the appropriate key chain with the right key string. All right. Remember, the passwords are never exchanged, only the hash is exchanged in this particular case. All right. So we've got authentication correctly configured now between two of our routers. Now we're going to take a look at what would I do if I'm running SHA authentication. So we're going to run SHA authentication between router 2 and router 5 and router 5 and router 4. And this one, because we're going to be running, well, actually we cannot do it. I was going to say we could use default interface in this particular case, AF interface default, but that would apply authentication to serial 2.0, and we're not running authentication on router 3. So that would break our adjacency between router 5 and router 3. So let's go ahead and set up our authentication for R4 to R5 and R2 to R5. All right. And I'm going to do it correctly the first time, and then I'm going to do it incorrectly the second time. My suggestion, guys, by the way, if you're doing a build in the CCIE lab, or if you're even doing troubleshooting in the CCIE lab, make sure that you have basic adjacencies. Make sure you have the appropriate configuration applied for your configurations, like without authentication is what I'm trying to say here. Authentication just adds another layer of complexity, and it's another layer that you end up having to troubleshoot. So if you can ensure that your adjacencies are valid and you're exchanging your topology information prior to implementing authentication, then you know if something breaks, it's directly related to authentication and it's not related to a misconfiguration with your EIGRP, underlying EIGRP configuration to establish your adjacencies. All right. So as long as you can see your neighbors, as long as you can verify your topology, you should be good to go. All right. The other thing that I'll point out, again, is that we're doing authentication and integrity, but we're not doing encryption. All right. We still see all the data in the packets that are flowing back and forth. So there are other things that we would implement to ensure that we're appropriately applying security to our topology. Things like passive interface, maybe on our switching environment, run some sort of IGMP snooping to limit the scope of where our EIGRP packets are going, and so on. So we'll talk about some of those concepts a little bit later on. All right. So let's go ahead and apply our configuration. Let's go to router number 2. Now in this particular case, we're going to be doing SHA authentication. And this is done under the named mode configuration. Remember, SHA authentication is not available with classic mode configuration. All right, IPv4 unicast, autonomous system number 1. Now I do want to apply the authentication to only this interface, serial 2.3. Okay, so actually we could do default in this case, and that's what we're going to do on router 4. I'll talk about that in a little bit with router 4's configuration. But for now, let's go ahead and apply our SHA authentication to serial 2.3 in this case. So we're going to go into AF interface. Oops. Interface serial 2.3, and we're going to say authentication mode, and in this case we're going to be using HMAC SHA 256, and notice that it wants us to apply a password directly to the authentication mode syntax, because in the case of SHA 256 we cannot reference the key chain. We have to specify the password directly on the authentication line. So let's do a CCIE-1. Actually, let's do CCIE-SHA. All right. Now, you should notice at this point that the adjacency would fail. Show IP EIGRP neighbors, right? We only have a single adjacency on serial 2.1. All right, so we've lost our adjacency on serial 2.3. Let's go ahead and do a debug. EIGRP packet. We'll also do a Wireshark capture. And we should see that we're getting an error from the other side. Let's see. Actually, you know what? It doesn't look like we're receiving anything from the other side just yet. I'm just seeing a bunch of Md5 authentication. So I'm guessing, let me do an undebug all real quick, that router 5 is not configured appropriately. Let's go ahead and make sure that the configuration is running. Show IP interface brief. Let's see. Oops. So serial 2.3 should be 1.6. That's correct. Serial 2.0 should be 3.6. That's correct. Let's see what else we got here. Ethernet 1.1 should be 2.6. Okay. Ethernet 1.0 doesn't need anything. All right. And we have our loopback, of course. But let me do a show IP protocols as well and see if we're actually running EIGRP. So we are running EIGRP in named mode configuration. But I still only have 2 neighbors on 2.0 and 1.1. That would actually make sense, but here, let me see show IP EIGRP interface. Show IP. So we are running EIGRP in all the interfaces. Let's go ahead and do a debug IP packet here. Debug EIGRP packet. And let's see if we see anything here to indicate that we're ignoring packets. So this is an interesting concept here. I'm seeing datagrams on serial 2.0 and Ethernet 1.1, but I'm not seeing any of the datagrams coming on serial 2.3. Let's go ahead and do a Wireshark capture. It could be that it's just simply not reporting that there's an authentication mismatch in this particular case. So let's go ahead and do a capture and see if we can see the SHA-enabled authentication or hello packets coming from 172.16.1.5 in this particular case. To load. All right. So, interesting. I'm not seeing any EIGRP datagrams coming over the interface. So, let's go ahead and verify our configuration. That's actually quite strange. Show IP EIGRP interface. We're definitely running EIGRP on serial 2.3. But we're not getting any timers. Show IP interface brief. 2.3 is up, down. Ah, there we go. So it's showing up, down status. Let me see if I got the cable 2.3 to 2.3. Let me check the other side real quick, which is R2. Ah, that would be the problem right there. Serial 2.3 is not configured on this particular router. So interface serial 2.3, IP address 172, And let me make sure I get it right. 16.1.5. There we go. Interface Ethernet 10, no IP address. Looks like we had some old configurations still sitting in there from one of our previous topologies. Do a no shut. Now we're not going to get our adjacency, but I should at least start seeing EIGRP datagrams going back and forth. So if I look at this datagram here, we can now see that we're running SHA-256. We're using key ID 0 in this case, and that happens to do with the fact that we're actually, you see the digest here is much, much larger, 256-bit digest as opposed to 128. But there's no key ID here because we're not referencing a key chain in this case. The key string is applied directly to the SHA-256 configuration. All right, so we are running authentication, which is a hex value of 2. Authentication type is 3. Type 0 would be no authentication. Type 2 would be Md5. Type 3 would be SHA. And we should now start to see on router number 5, show debug. I believe I turned it off. So debug EIGRP packet. And I should start to see hellos coming and going. So I'm sending a hello, sending hello, sending hello, receiving hello. But we are seeing hellos at least, or sending hellos at least on serial 2.3 in this particular case. So let me go over to router number 2 and do a debug EIGRP packet and see if we can see any indication that we have an authentication missing in this particular case. There we go. So undebug all. And we can see here I ignored the packet from serial 2.3 because it's missing authentication or the key chain is missing. So it's saying here, you know what? I don't even know what authentication the other router is trying to run because it's not sending me any authentication variables because it's not running authentication. So I don't know if there's not a keychain applied or if it's actually just not running authentication altogether. All right, let's go ahead and fix that problem. And we're going to apply authentication to, let's stop this capture. We're going to apply authentication to this interface in our address family mode configuration. All right, so let's go to router 5, config T, router EIGRP Ccie, address family IPv4, unicast autonomous system number 1, AF interface. Now, actually, I could, because in preparation for what we're going to be doing for this link as well, we're going to be doing SHA authentication on this router. So I'm going to go ahead and apply the authentication to serial 2.3 and Ethernet 1.1 in this case, since we're going to end up running authentication on those interfaces anyway. Unfortunately, I can't do a group of interfaces, so I have to authentication mode SHA, HMAC SHA 256 CCIE -SHA, and we should get an adjacency. I believe that's what, there we go. That was a key that I used. And I'm going to also apply this on Ethernet 1.1. And let's take a look at the configuration. So you notice we got an error. Authentication is configured. The neighbor went down. Now that is not very descriptive, but it does indicate that there's an issue with authentication between that peer. So show run pipe section router. Okay. So on router 4, we're running classic mode or named mode configuration. We've actually applied classic authentication to Ethernet 1.1. And what I'm going to do in this case, I know that's opposite of what our diagram says here. We were going to apply our classic configuration to default, but let's go ahead and switch this over just to make sure it matches our configuration. Ethernet 1.1, and we're going to do our SHA authentication default in this case. Now, keep in mind when you're doing AF interface default in your AF mode configuration that it applies to every interface. Not something we normally would do. We would probably try and keep our configurations consistent, but I want to demonstrate a concept here. All right. So router EIGRP, Ccie, and let's go into our address family IPv4, unicast, autonomous system number 1. And I'm going to do AF interface default in this case, authentication mode, HMAC, CCIE-SHA. All right, so we should get our adjacency back with router number 5. And here's the point that I wanted to make by mixing up this configuration a little bit. Is that when you do apply the configurations, anything that's going to be applied to a specific interface is always going to override whatever's applied to the default interface. So and this applies to just about anything that we can apply, any configuration we can apply in the AF interface sub-configuration context. Default configurations are always overridden by whatever is applied in the specific AF interface that we're configuring, in this case Ethernet 1.1. So we didn't break our adjacency with router 1 because we had Md5 and keychain CCIE applied on that interface. And we were able to establish our adjacency with router 5 because we applied the HMAC SHA-256 authentication method to our default interface. Does that make sense? Okay. So we're done. We're done with at least that part of the configuration. We've got authentication running on essentially the outside routers here. We decided not to run authentication on router 3. And we're using the appropriate authentication strings and so on. Now, what happens if I don't use the right key ID? So I'm going to go into router number 2. And I'll do a show keychain real quick. All right. And I'm going to go into keychain CCIE, and I'm going to do no key 1. All right. Do show run. Why did it drop me out of there? That's weird. It dropped me up back into global config. Do show run section key. So you can see in this case we have a keychain. Actually, it deleted the whole keychain, it looks like. Makes sense. If there's no valid key within the keychain, there's no reason to have the keychain. So let's go ahead and create the keychain again. In this case, I'm going to do key 2, and I'm going to do key string CCIE-1. All right. Now the point of this is to indicate now that we're sending key ID 2, and router 1 should indicate that it's receiving the wrong key ID. So if I do a debug EIGRP packet, I should see that I'm receiving the wrong key ID and the packet is being invalidated for that particular reason. And we see that right here at the top. Authentication key ID 2 is received. The key is not defined, so we ignored the packet because of invalid authentication configurations. All right? Pretty straightforward. And if I was doing a Wireshark capture, of course, you'd see that key ID 2 is being used. So let's do keychain CCIE, key 1, key string, CCIE-1, key 2, key string, CCIE-2, and key 3, key string, CCIE-3. All right, so now if I do a show run pipe section key, I can see that I have 3 keys configured, CCIE-1, CCIE-2, and CCIE-3. All right, if I do a show key chain, you can see that all the keys are valid because I didn't apply a send or an accept lifetime on those particular keys. I'm going to do the same thing on router 1, config T, keychain CCIE, key 2, key string CCIE-2, key 3, key string CCIE-3. Show keychain, and we can see again we have our 3 keys. All right, in fact, let me get rid of that no keychain CCIE underscore temp. Oops.
Hey, Scott.
Yes, sir.
You explained this before, but I'm still a little confused. So if you have on one router, it has the first key is CCIE 3. Would that just automatically connect to the third key on the other router?
No, because we never send the string. We don't verify the data we're receiving against all of our valid keys. We verify it against the key that matches the key ID. So if I've got in our case, we've got the 3 keys configured on each router, 1, 2, and 3. As long as those keys are all valid, we'll always use key 1 to send data. The lowest key ID is always used. Now, let's say that in this case, key 1 and key 2 are not valid, but the key string here is CCIE-3. But in this case, all 3 of these keys are valid. I will send with key 3, okay? And as long as this 3, which gets matched against that key, as long as this key string matches the key string that was used on the other side, then I can validate that datagram. But if, let's say this...
If the password's not the same, though, on 1 and 2, but otherwise it's valid, but that won't work.
Right. So let's say that key 1 in this case is CCIE-3, and key 3 over here is CCIE-3. The problem is when I send my datagram, I'm referencing key ID 3. And because I don't have a key ID 3 on this side, then there's no way for me to validate the authentication because I don't have a key 3 to verify it against. I'm not looking at the key string, I'm looking at the key ID. Does that make sense?
Yep, thanks.
No problem. Okay. So in this case, if I do a show keychain, we can see that we actually have 3 valid keys. And it's kind of pointless, right? Because key 2 and key 3 would never be used unless I had a situation like this where I had multiple routers that I'm authenticating against. And for whatever reason, I've decided that I'm going to have key 1 on this router, key 2 on this router, and key 3 on this router. All right, and this is going to be CCIE-1, and this will be CCIE-2, and this will be CCIE-3. As long as I have all 3 of those keys configured here, all right, well, actually, that's not going to work, is it? It'll work for receiving, but it won't work for sending, okay? So what I would have to do in this case is I would have to set the send lifetime for each of these keys. I would have to make key 3 valid for this interface. I'd have to make key 2 valid for that interface to send, and I'd have to make key 1 valid for that interface to send. Because again, remember, if all 3 keys are valid, I'm only going to be sending with key 1 in this case. Now, as far as receiving goes, it doesn't matter how I'm receiving because I'm going to match the receiving key ID against any valid key in my keychain. All right. So if everybody is sending their individually configured keys, CCIE-1, CCIE-2, and CCIE-3, as long as those 3 keys are valid here, I can match the key ID 1 against that key, and key ID 2 against that key, and then key ID 3 against that key. And as long as they're active and valid, we can authenticate that way. It'd be actually kind of complicated to do it this way, and you don't really gain much benefit from this. Because again, you know, you're still protecting the data the same way, regardless of whatever the key is. But one of the things we do want to talk about is the concept of rotating keys or key rotation. Now again, this would only apply to our Md5 authentication. So let's say in this case, I've got key 1, key 2, and key 3. And this is my time scale, 1, 2, 3, 4, 5, whatever, 4, 5. All right, so I've got my, we'll just call these minutes or whatever they are. So when we're defining our keys and time, when we're defining our keys, we can specify two different values. We can specify what keys are valid for sending and what keys are valid for receiving. We call this a send lifetime and an accept lifetime. All right, so what keys are valid for sending and receiving? And so we could say, okay, for example, for key 1, let's go ahead and make that key valid up to 2 minutes for sending. Okay, and then key 2, let's go ahead and make that key up to 4 minutes for sending. And then for key 3, let's go ahead and make that infinite for sending. All right. So if you look at the breakdown here, this key has a specific lifetime. And when this lifetime expires, the next key goes into effect. When this lifetime expires, the next key goes into effect, and so on. The problem with this particular scenario is that you may run into a situation where a particular key is no longer valid for a millisecond or a second or a few seconds because the routers might not have the exact same time configured on them. All right. Now we try to use NTP or PPT or our precision protocol or our network time protocol to make sure that the times match, but you always want to build in, especially if you're doing any kind of key rotation, you always want to build in some overlap to ensure that you have valid keys. All right, so we would actually add in here maybe a little bit of overlap here and here, a little bit here, a little bit here, so that we have this threshold where the keys are valid for sending and accepting. I didn't draw the accept keys here, but we want to make sure that as they're rotating, that the keys that are being sent could be accepted as well. It's a little confusing, but we'll go ahead and match that up in our configuration here in a little bit. We're only going to do this on a couple of routers. Remember, this also only applies to keychains, which is Md5 authentication. You would not be able to do this with SHA authentication. There's simply only a single key with SHA authentication. All right, so we're going to go ahead and configure it in our topology here. Because we're already running Md5 authentication between R1 and R2, let's go ahead and set up key rotation on a 3-minute interval. With 3 keys. All right, between these peers here. Now, obviously, you're not going to do a 3-minute interval in the case of the real world. What would you do typically in the real world? You might do maybe 1 month or 1 quarter. That people always ask me, what should I do from a key rotation perspective if I'm running Md5? Well, frankly, I would say if you're running named mode configuration, just run SHA. Because the only thing that we're concerned about here is somebody using cryptanalysis to discover what our key is. And the only way to do that is through brute force by going through different hashes and trying to verify the hashes. So if we're using SHA 256, it somewhat makes the brute force process infeasible. Reversing the hash is not really that feasible. The work factor is way too high in that particular case. But if you're not running named mode configuration, you have to run Md5. So in that case, you may want to run key rotation. Depending on the strength of the key is going to determine the strength of the algorithm, right? So if I'm using a key like Ccie, that's not going to be a very strong process. And cryptanalysis should be able to discover that key in a relatively short amount of time. But so it's more important that you use a strong key string than to do key rotation. Quite frankly, key rotation is not something that is necessary if you're using a strong authentication key. Nonetheless, we'll take a loop at it so that we can ensure that we're getting appropriate key rotation. I'm going to configure router 1 as an NTP server. And I'll just give it a stratum of 1, show IP interface brief. And we're going to just get our time from this loopback interface. So let's do a config t NTP source loopback. Yeah, let's do 192.168.1.1. All right, source interface. What the heck is going on? Oh, loopback 0. There we go. All right, so we're going to source our NTP traffic from loopback 0, and let's just go ahead and get config t NTP master NTP server. Excuse me, 192.168 dot. Let's see, 1.1. Let me just copy this here. All right, so we'll go ahead and configure that on the other routers here. And last one. Show NTP associations. All right, looks like we're okay. Show NTP status. Clock is synchronized. Okay, so let's go ahead and do a show clock on, let's make sure, actually, I guess I didn't really have to do it on all of them. We're only doing this between router 1 and router 2, so let me see, show NTP status synchronized. All right, show clock. So let's go ahead and set our clock. Clock set 000000 January 1st, 2000. All right. And let's see. Oops. Show clock. Didn't synchronize. Why didn't it synchronize? It might take a little bit. It should synchronize here in a little bit, though. So our clock here is correct, 32 seconds in. All right. So let's say, let's come up with a scenario here. And it's kind of important that we kind of paste this into Notepad here first, because it gets a little confusing when we're trying to define the times. So let's set for key 1. And let's do an accept lifetime of 000000 January 1st, 2000, and let's end that at 05/30 January 1, 2000. And let's do a send lifetime in this case of 000000 January 1st, 2000, and do the same thing 0007 or 05 00 January 1st, 2000. All right, so I'm just going to copy this, and we're going to start to rotate through our keys. So this key is going to last till 5 minutes and 30 seconds, and key 2, from a send lifetime perspective, let's see here, is going to start at 5. So it's going to be a little bit overlap from the accept lifetime on this side. And let's do this one up to 10 minutes. Okay. Now the accept lifetime, we're going to go ahead and set that to 5:30. let's see. This is where it gets a little confusing. Let's start with one key. Okay, I'll do the other keys in a minute. So, and actually, let's just, to make it simpler, let's go ahead and just let's do all three keys, but let's do the accept lifetime first, and then we'll do the send lifetime. So key 2 and key 3. So if we're following the logic, this key is going to be valid up to 5 minutes and 30 seconds. But I do want some overlap. So key number 2 is going to start at 5 minutes. So there's a 30-second overlap there, and we'll just put this guy up to 10 minutes and 0 seconds. Okay, 30 seconds, excuse me. And then this key is going to start at 10 minutes, and then we're going to go ahead and set this one to infinite. Not that you would do that. You would end up, usually you'd have at least one key that's going to run to infinite because you don't want EIGRP to break. But if you were doing this rotation, say every month, for example, you'd want to ensure that that there's at least one key valid at the end of the cycle, just in case there's a misconfiguration or you haven't added the additional keys for the next 12 months or whatever it might be. So if this makes sense, we're accepting this key starting at this time up to 5 minutes and 30 seconds, and then we're accepting this key and so on. So let me go ahead and put this in first. Let's do a show clock. We're at 4 minutes and 26 seconds here. Not sure why the clock is not synchronizing here. There we go. All right. So it looks like we missed our time frame here. So I'm going to make a modification to this real quick. We're going to make this up to 6:30 and 6 in this particular case. So let's go ahead and paste this in. Config T, keychain, Ccie. All right. And let's do the same thing on router 1. Config T, keychain, Ccie. All right. Show keychain. So we should see in this case that, forget the send lifetime for now. This key is valid for sending, for accepting. This key is valid for accepting at 10:30 or starting at 6. And this key is valid starting at 10. So we can see that only one key is presently valid for sending and for accepting. Now, because we didn't specify a lifetime for sending, it automatically provided us an infinite lifetime for sending. All right, but we should see in this case, there's our window where both keys are valid for about 30 seconds. And then after a certain time, after 6 minutes and 30 seconds, we should see that, so 2 more seconds. Yep. So you'll notice here there was a discrepancy in time. Very important. Our window probably should have been a little bit larger. So if I do a show clock here, 6:45, and I do a show clock here, 6:51. So there is a bit of a discrepancy, but actually this is the other neighbor. Remember we're rotating through the keys now. So forget that message. We're still peers with router 2, show IP EIGRP neighbor. So we're still peers. Actually, let me see. Router 2 lost its peering relationship. So let's see why. Show keychain. So key 2 is valid now until 10:30. Show keychain. And key 2 is valid here. That's what's happening. So what's happening in this case, and this is actually probably a good thing that it's happening, is that key 2 is valid for accepting data, but key 1 is no longer valid for accepting data. Does that make sense? But because key 1 is valid for sending, whenever I'm sending data back and forth, I'm going to use the first valid key to send data, but I cannot accept that key because it's no longer valid within the window. So we definitely want to make sure our send and accept lifetimes are synchronous. So let's go ahead and do a send lifetime. Because when we're rotating through the keys, we want to make sure that the same key is being used for sending as it would be for receiving. So keychain Ccie. All right, and we'll go to router 2, config T, keychain Ccie. And you'll notice that we actually got our adjacency. So now if I do a show keychain, we can see that we're matched up now. The key that we're using to send data is the same key that we're using to accept the data. So for another, let's see, show clock. For another minute or so, or a little bit less than a minute, actually just a little bit more than a minute actually, these keys are going to be valid. So we should see here pretty soon that the third key in about 3 seconds, 2, 1, 0, that third key should become valid as well. So we should already be in that window. Not quite. We've got about 15 seconds left because this one starts at 10. So let's see, 7 seconds, 6, 5, 4, 3, 2, 1. All right, there we go. So now we're in the overlapping window where key 2 and key 3 are both valid, and we're going to be rotating, and then in about 2 more seconds, we should see, maybe 3 or 4 more seconds, we should see key 2 is no longer going to be valid, and we're only going to be using key 3 in this particular case. Now, how much overlap should you provide? Some people like to do like a day. They don't want to, it's not going to be based on a certain number of minutes or seconds. Because again, in order for our adjacencies not to lose, or in order for us not to lose our adjacencies, we need to make sure that the keys are valid on both peers, right? So if we're basing it on a 10-second window or a 30-second window and the clocks are off by 30 seconds, you could lose an adjacency in that particular case. All right. So typically we'll make the send and accept lifetimes the same because again, if you have multiple keys that are valid for sending, you're going to use the very first key in the key list. You could get really creative and you could kind of mix and match sending and receiving keys, use asymmetric keys for authentication, but at least for sending anyway, but that gets really, really complicated. Okay. So that's the concept of rotating through different keys. Now I've done this before with a customer. They requested that we configure this, and we essentially set up 12 keys, one for each month, and we had an 8-hour overlap between the keys. So for 8 hours, key 1 and key 2 would be valid, and then after that 8-hour window, only key 2 would be valid. And then at the end of the cycle, on the 12th key, we went ahead and set that key to infinite, and then when that key was active, we went ahead and created another set of 12 keys for the following year. I know it seems like a lot of work. That's just what the customer requested in this particular case, but we did make the last key infinite just to be sure that in case somebody forgot that this was something that was being configured, that a month later you wouldn't lose your adjacencies because that 12th key was only valid for a month. Does that make sense? So that's the concept of key rotation. Like I said, it doesn't exist in the concept of SHA authentication with named mode configuration. All right. I guess that's about it. We covered all 3 lessons. I kind of merged them together because I think it makes sense. We covered, let's go back to our list here. We covered classic authentication using MD5, and we talked about automatic key rotation. And we talked about named mode authentication using SHA-256 or even classic MD5 in our named mode configuration. So great, we did 3.5 hours in an hour and a half. That's actually pretty good. Do you guys have any questions about this particular configuration?
No, it seems pretty clear.
Yep, it's pretty clear. It's obviously something that you guys need to be familiar with, both for written and lab. Like I said, I don't know if you're going to be doing any named configurations in the lab. But you've already seen it enough times. I think you guys would be pretty comfortable if you're faced with, address family mode configuration as opposed to classic mode configuration. So what are we going to talk about next time? Our next goal is to cover essentially these 2 topics in our next session, the EIGRP summarization. I don't think it'll take 2 hours for that. There's a few things that I want to show you guys with that. And then traffic engineering with summarization. Is an interesting concept, but it's not very practical in a sense. We're influencing route selection based on prefix length rather than based on metrics by utilizing summarization to force routes to take a different path. But that's going to be an interesting topic. And then we really only have 2 other EIGRP topics, DMVPN and stub routing. All right. So we'll wrap up.